Okay, so today we're going to talk about this thing called calorimetry. Calorimetry is actually made up of two words, calor and metry. Metry doesn't mean you're trying really hard. It means something else. What do you think calor means? Oh, yeah, hot. What about metry? The measurement. Very good. So geometry is the measurement of angles. Geometry, right? And so when you see this kind of root, it means that it's a measurement. So calorimetry is actually the measurement of heat. But how do we do this? There's actually a standard way of measuring heat. And we're going to take advantage of water. We typically use water to capture this heat. So we typically burn something or have something that's hot, and we place it into a water chamber, a chamber that basically allows the water to absorb all the heat. And the way this works is we measure the temperature of the water, and we know the mass of the water, and so we can actually calculate how much heat the water actually absorbed. Because we'll have a delta T for the water, we know the specific heat of the water, and we have the mass of the water. So we can use MCAT for the water. But if my system is really well insulated, like I have a bunch of styrofoam shielding it from losing heat to the environment, I can say that the water should absorb the same amount of heat that is lost by the object. And we can make this argument if it's well insulated. Okay? So let's take a look at an example. Here's my example. 24 grams of an unknown metal, we actually don't know what the metal is at 100 degrees Celsius. So I've heated it up to 100 degrees Celsius. That sounds really hard to do. How do I know that my metal is at 100 degrees Celsius? That is boiling temperature. The boiling temperature of what? Of water. Metal doesn't boil at 100 degrees Celsius. That's too low. If metal boiled at 100 degrees Celsius, then your pan should turn into gas when you're trying to make spaghetti. But it doesn't. The water will boil, but your metal does not. In fact, your metal doesn't even melt at 100 degrees Celsius. So this metal is at 100 degrees Celsius because it's probably sitting in boiling water. Okay, are you imagining this? Okay, so I'm going to take this hot metal and I'm going to transfer it into a styrofoam cup that contains 200 grams of water. This water is at room temperature, so it's about 20 degrees Celsius. What do you expect the water will do when I throw a hot piece of metal in it? The water should get warmer, but the metal should get colder. When does that heat transfer stop? When they are the same temperature. As long as one's hotter than the other, heat will continue to flow because heat flows from hot to cold. Once they're the same temperature, then heat flow stops. What temperature do you think it will be? 22 degrees Celsius. Huh. But wait, didn't water start off at 20 and the metal start at 100? How come they ended up at 22 and not like 40 or 50? What happened? Any ideas? Well, for one, look at the masses. How much mass was the metal? And the water? So the water was much more, so it takes more energy to heat up that water. What else? What other things are different? The temperature is different, the delta T's are different, but, one more thing. Think about your MCAT equation. The mass is different, the delta T is different, but so is the specific heat. We know that water has a much higher specific heat than most metals, and so it's more expensive to heat. And so that's why the water only goes up by 2 degrees, whereas the metal goes down by like 70 degrees. All right? So to help you understand this, I'm going to show you a picture. What happens to the hot metal? I put it inside the water, like this. Ooh. At this point, the metal cools down, and water heats up. And when does that stop? When they reach the equal temperature, which happens to be 20 degrees Celsius. How was that? Okay. So, what's the point of all of this? Well, what I want you to do is to calculate the specific heat of this metal. Because we don't know what metal it is, if we can find the specific heat, then I can look on that chart and we can figure out what metal it is, like our opener today. So, let's set up an equation for this. The way this is going to work is we're going to set up something called a double MCAT equation. Okay, so this is what I'm going to say. Q of the water should be equal to Q of the metal. Except Q of the water is actually equal to the negative Q of the metal, because metal should have a negative Q and water should have a positive Q, because one's losing and one's gaining. If I apply absolute value over Q metal, then they should be equal values. Are we okay with this? But what is the equation that we've been working with this whole time? MCAT. Q of water is actually equal to M water times the specific heat of water times the delta T of the water. And we can set this equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. This is what I call the double MCAT equation. We have two MCATs that are equal to each other, and all we have to do is plug in everything we know, which is actually very hard. So I'm going to assist you. I'm going to change my color to blue, and I'm going to circle the first item here, and I'm going to ask you, which of these variables is that? 24.0 grams. That tells me it's a mass, but is it the mass of the metal or the mass of the water? Is the mass of the metal. So that's M for mass and M for metal. That's MM. How was that? Let's circle the second one. This is T1, or the starting temperature of the metal. So T1M. Do you think you can label everything else? Yeah. Okay, go ahead and do that. Okay, so we've labeled all of our items, and now we're going to plug in our labels into the correct locations on our double MCAT equation. Go ahead and do this now. Let's check in. What did you plug in for your MW? 200.0 200.0 Gs. And what did you plug in for your specific heat of water? 4.184 joules per grams degrees Celsius. And what's the delta T for water? 2.0 degrees Celsius. It shouldn't be negative because in this case it's actually increasing in temperature. We're going from 20 to 22. It should be a positive 2.0. Now, on the other side, do we have a mass of metal? Yeah. What do you think, Brendan? Mass of metal? 24.0 grams. What about the specific heat of the metal? Unknown. We don't even know what metal it is, so we can't even look this up on a table. But do we have the delta T for the metal?
Yeah. Yes.
Yeah. So technically it's negative 78. But I'm just going to write 78 degrees Celsius because I'm going to apply an absolute value rule here. I want them to match because, you know, they're technically supposed to be negative, but I want them to match. So I'm going to go ahead and apply a specific, an absolute value here. Yeah.
So they're negative to metal? Is that why?
No. Now that we've filled in all of these pieces, I'd like you now to solve for the missing variable. Go. Okay, let's check in. How do I isolate the variable? I'm going to divide the right side by 24.0 grams, and I'm going to divide the left side by 24.0 grams. How else do I need to isolate the variable?
You divide 78.0.
I also need to divide 78.0 degrees Celsius on both sides. And you can see that degrees Celsius cancels, and so does grams. What is left behind? Joules per grams degrees Celsius. But how do I input this in my calculator? Well, it would be 200 times 4.184 times 2.0 divided by 24.0 and divided by 78.0. That's a double division. We've done these things in the past, right? So when you're done, C metal is 0.89 joules per gram degrees Celsius. However, this is not what the question is asking you to find, is it? No. We still need to check our little chart. And so what I'm going to do is I'm going to pull up the chart from our opener. And if you look on this opener chart, we can check which one is closest to 0.89. And this happens to be aluminum.